I think the story is a bit more of a depressing end than the start of the story.
You're listening to The Cosmic Cast.
Hello, and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. Your hosts today, it's me, Marissa Lowe, joined by Ricky Bahir.
Hello.
John Perney-Fisher.
Hello.
And our special guest today is final year PhD student at the University of Manchester, Emily Bamber.
Hello.
Hello, Emily. How are you doing today?
Good, thanks. Yourself?
Yeah, pretty good. Well, thanks very much for coming on to speak to us today.
Thanks for having me.
Lovely. So you study volcanoes, very exciting topic. More specifically, you look at basaltic Plinian eruptions, I believe. So would you mind giving us a bit of background as to what your PhD project is, please?
Sure. So my research focused on basaltic volcanoes. So these are volcanoes that typically erupt basaltic magmas, so magmas that have a low silica content. So they're quite low in viscosity, and then they normally produce what we would call an effusive eruption at the surface. So say you have the lava flows, and also low explosivity eruptions. So some typical examples are in Iceland and Kilauea. So normally these dark coloured lava flows that extend from the summit of the volcano. What I'm specifically looking at is Plinian eruptions. So these are rare at these systems. These are highly explosive members of volcanism, so producing large amounts of ash, an eruption column that's ejected tens of kilometres into the atmosphere, and also a lot of more deposits associated with explosive activity, such as pyroclastics and scoria.
So would your sort of classic Plinian volcano be like Mount St Helens or something?
Yes, Mount St Helens, also Pinatubo in 1991.
Yeah, all these big beefy volcanoes, I guess.
Yes, with the large eruption column towering above the summit as well. So both examples of those are not basaltic systems. So these are more evolved in their composition. There's more silica.
Andesitic, is that right?
Yes, or dacitic, yes.
Dacitic, yeah.
So they are higher in what we call viscosity. So in general terms, just resistance to flow. So it's more likely that these magmas get stuck during ascent. You build up pressure, and then you have a large explosive eruption. And this process is what we term fragmentation. So you have the breaking apart of this material, which produces the large ash column seen at the summit of the volcano, which is not what we see very often for basaltic systems.
Yeah, so you said these are very rare in volcanic history. Roughly how many cases do we have recorded of basaltic Plinian eruptions?
So for historical records, there's two significant examples. So the Aetna 122 BC eruption. So Aetna is in Sicily, located very close to Catania. So there's some documents from that time of a large eruption of Aetna, which is the Plinian eruption. And then also Tarawera in 1886, there's records there of this large volcano producing an eruption that had some quite diverse activity, some large explosive columns, some less so. For the geological record, we have some stretching further back. So with Masaya volcano in Nicaragua. And then so the geological record, that's what we have. So with further study, we might find more examples of basaltic Plinian eruptions as well.
Okay. So would like the volcanic history more be like human records of things? So like, people writing things down or maybe drawing beautiful ash columns or something, whereas I suppose the geologic record is more, you've looked through logs of volcanic rock or something like that?
Yes. Okay. some typical sources for historical records will be like written documents, say like when you erupted as well, 79 AD. We do have some like written documentation of what this actually looked like at the time. So the type of deposits, was it ash or scoria? We have some examples of that. For Tarawera, there is also some kind of more artistic depictions of the eruption itself as well, that were painted shortly after the time.
Yes, because am I right in saying Plinian Eruptions, that's the name that came from, was it Pliny the Elder, who apparently looked over at Vesuvius as it was erupting in 79 AD, and I think the story is a bit more of a depressing end than the start of the story. Yeah.
Yes. So that's kind of like our example of a Plinian eruption, hence the name as well.
Yeah. So it's interesting then these are volcanoes though that don't necessarily, they have different eruptive styles as well. Then I suppose you have your more, because I guess so Aetna does a lot of more effusive basaltic volcanism, doesn't it? I suppose, as well as this historical record of the Plinian style.
Yes. So more effusive activity. So yes, like the lava flows. There's low explosive eruptions as well. And in between, we have subplinian eruptions, which have a similar behavior in terms of they are explosive. There is a deposit that has ash and scoria, which are where you're fragmenting this magma, as explained earlier, but they are smaller in magnitude. So the volume of the deposit itself is smaller. So the classification for the Plinian case comes from the volume of the deposit, so what's ejected from the volcano, and also the column height, so how high into the atmosphere that this eruption column extends to. And Aetna has exhibited examples of these activities through time. There is variation, yes.
Yeah. And when they have these explosive eruptions, is the material that's produced not basaltic, or is it still basaltic material?
Yeah, it's basaltic.
Okay, right.
Yeah, it can also be basaltic andesitic as well, which is more evolved than, say, the basalt. So the basalt will be, say, I think 47% silica up to around 51, 52. The basaltic andesite then comes after this. And there are variations also in this due to how much alkalis there are in this magma, so sodium, potassium. This can also change the behavior of the magma and its chemical composition. So there is some variation within this basaltic bracket, say.
So of the different eruptions and volcanoes that we've mentioned so far, have you gotten to visit any of them, or which one is your PhD mostly focused on?
So I'm focused on 2 volcanoes, which I've explained earlier, which is Masaya volcano, so this is located in Nicaragua. So this is a caldera complex system. So its structure is a bit different. So there's been a collapse through time from the volcanic activity. So it doesn't form this big kind of cone-shaped volcano, which we term stratovolcano. So it has less elevation, and then at the center is a lava lake, which appears and disappears through time. So I have done fieldwork at Masaya, but to collect samples of 2 basaltic Plinian eruptions from this system. So the Masaya AAA eruption, which is 2,000 years ago, and then also the Fontana Lapilli eruption, which is 60,000 years ago. So these are the eruptions that we recognize in geological records as well, so stretching back 60,000 years in this case. And I'm also doing some work on Aetna, on the 122 BC eruption. So I've done field work in both cases.
Yeah, that sounds really cool. So it was field work in some of these areas quite challenging then? I mean, are you really sort of mounting the edifices of these volcanoes and really getting up there? Or?
Mostly in a car. Because Messiah itself, and the elevation is quite low, and there is a path to the summit. So we did drive to the summit to see the volcano there, and then also the case of Plinian eruptions, the deposits can be ejected quite far from the volcano. So you're usually looking at if you're looking at proximal deposits, so a few kilometers from that volcano, there's a nice deposit of the eruption that you're interested in, and also further away, like the distal case, so tens of kilometers. Also in Aetna, we drove to the top as well, so partially up the way to see the volcano itself, and then the localities are usually further down the slope, because especially with the case of Aetna, where there's been quite a lot of activity recently, a lot of that deposit can be covered by newer examples of activity or be removed through time.
Is Aetna still erupting today? It's been erupting for a hell of a long time, hasn't it?
Yes, I think there was another example of one of these large magnitude eruptions 4,000 years ago. Was it 4,000 BC that I'm aware of? And it does erupt quite frequently now as well, or it's in a more persistent type of activity. So it erupts quite frequently.
So once you get these samples, by the way, when you're getting these samples, are you allowed to just pick up a sample and take it with you, or I assume do they just let you do that, or are there some steps you have to take beforehand before you start taking samples?
It's just you, Ricky. You're not allowed to pick up any rocks.
That's what fair enough. Yeah.
I think normally when we go to do sampling, we're in contact with the local contact in that area. So the organizations that are responsible for monitoring the activity of the volcano, in both cases, so they know the deposits. So kind of communicating with them and going with them to see the locality, and then I guess what you're interested in looking at, like how much material would you need, is always a good question. So just to take that is fine. So to have a sampling strategy before you go is good.
Okay, so you've collected these rocks then, and now you're back at Manchester. What's the next steps then, and what do you do with these rocks?
I use several instruments to kind of look at what these samples can tell us about how the volcano works in that particular case. So for the Plinian eruption, so the pre-eruptive conditions, the syneruptive conditions, these are the conditions essentially in the magma chamber before eruption, and also during the ascent to the surface, so within the conduit. So the conduit.
Can I just ask, are you trying to figure out why these explosive eruptions are occurring where there's basalt, or is that a question that's people already know the answer to? Obviously, because that's atypical, isn't it, for a basaltic eruption to be so explosive? So are you working at the frontier of trying to figure out why that's happening?
So yeah, they've been looked at before as well. Like there's a kind of a whole body of literature that looks at this question. I would say it's quite a big question to answer. Yes. So some kind of ideas of why this magma might erupt more explosively. So it's truly at the heart of understanding what the eruptive conditions are. Yes, there's been studies that are looking at the role of crystallization, or the role of the pre-eruptive volatile content, so how much gas is stored just before eruption, and also the mechanism itself, how this magma can actually fragment if it's of low viscosity. So how can we produce a large volume ash and scoria deposit?
It's probably worth thinking also, a lot of these volcanoes, there's obviously lots of settlements and lots of people living near them. And I suppose if we do have the story of, oh, basaltic volcanoes, they're just going to produce like effusive lava flows, that's not too dangerous, you know, that's not going to cover a huge range. We're relatively safe. I suppose part of this, the work that you're doing, Emily, is going, no, they can be explosive. They can be shooting ash a lot further than we think. So yeah, I suppose there's a big importance in this kind of research. So yeah, it's very cool you're doing this.
Yeah, I think it's a great question to be looking at for that reason. Yes, like understanding why this may happen, or why this may happen at these systems instead, whether it's likely to happen again in these systems are good questions to be answered, because yeah, it changes in some way how you perceive the hazard of the volcano, like you just explained, Marissa.
So once you've got the samples, as we were discussing before I rudely interrupted you, you take them back to the lab, and then what analysis do you do to figure out these conditions in the magma chamber, for instance?
So I think there's two things I'm quite interested in looking at, is the chemistry of the sample and also the texture, so how it looks, what minerals are there, how much of them, what is their proportion, what shape are they, are all interesting aspects to look at, which can tell you what the condition was before eruption or during eruption. It can give you an idea of the pre-eruptive storage conditions. So if we're aware of the sample chemistry, the pre-eruptive temperature, the pre-eruptive pressure, which is also an idea of the depths of storage just before eruption. Quantifying volatiles are also very interesting to look at. So mainly water, CO2, see how these will influence the actual eruption dynamics. And then how many crystals are there, as this can also influence the syneruptive behavior of the magma, say how easy it is to flow. So if it becomes more viscous, if there's more crystals. So there are a few instruments that can give us this information. So the electron microprobe is used to kind of investigate the chemistry of the minerals that you have in your sample, or the chemistry of the glass, which is essentially the liquid part, which is cooled very fast. And also some melt inclusions. So again, the liquid, but these are actually trapped inside crystals themselves. And also a similar technique, which is the SEM, which is scanning electron microscopy, to take some images of your sample. So you can start to look at some microtextual things as well.
So it sounds like a lot of the things you're looking at are really small. What sort of, how much detail can you pick out from all these crystals?
Yes, they're very small. I think it's become a characteristic of my samples, is everything's quite small. So I'm able to look at crystals quite well that are tens of microns in size or less.
Wow.
With these instruments, which is a huge advantage, because a lot of my samples are quite crystalline, but on a very, very fine scale.
So have you just been using instruments in Manchester, or have you gone further afield to use some other cool pieces of instrumentation?
Yes, so I've done work in Manchester with these instruments, but I've also had the opportunity to go to synchrotron.
Wow.
Which is to carry on looking at these samples from a different perspective, to look at them in 3D.
Yeah, so you said they build up sort of more 3D pictures of your sample rather than 2D ones, which you've been getting from the other instruments in Manchester. That's really cool.
Yes.
So is that a 3D mineralogical image of them, or just literally a 3D high resolution image?
Yeah, so in this case, Xray MicroCT is similar to technique you can take in radiographs. So what we was used in medical imaging. It's quite similar to this, say if you have a broken bone, taking an image of this. In the case of Xray MicroCT, you're imaging, in my case anyway, the whole sample. So this will be a whole scoria, which is a few millimeters in size. And you're essentially taking a series of radiographs, but rotating your sample whilst you are taking these. So you have the X-ray, which is passed through the sample to a detector on the other side. And essentially, if you have a multi-phase material, such as the scoria in this case, different parts of the sample will absorb X-rays to a different degree. And then you start to build up a series of radiographs based on this different absorption, where you can start to pick out different features. And because you're rotating the sample, you can then take all of these slices in 2D to bring them together to make a 3D image, which is what you're interested in looking at. And then there's a lot of other techniques where you can then take this 3D image to do some more analysis on this. So looking at segmenting features of interest and some more quantitative procedures as well.
Yeah, how was it working down at Diamond then? Because I remember before you were going, you were all talking about a 24-hour schedule and who was going to take the night shifts.
Bloody hell.
Intense. Less sleep, I think, yeah, because you work in a series of shifts, and when you work there, you have like the whole day, effectively all 24 hours for when you are there. So it's working out who likes to work at night. Is always a good conversation, yeah.
Is that just due to efficiency? Do they just want as many people to use it because people need to use it a lot, or?
Yeah, I think just to make the most of your time there, because the beam will be on. Yeah. So it's best if you have a long running experiment. In some cases I have, that was fine. If they're a bit shorter, a few hours, then it's good to stay awake.
Yeah.
Wow. So I guess it's quite manual then. You can't just like set up a run and leave it for X hours or whatever.
Yeah, to keep checking on how it's proceeding, if you're getting the good images, if the conditions that you've set are good, it's good to keep an eye on the experiment.
Yeah.
Emily, how far through your PhD are you?
I'm in my fourth year.
Fourth year, okay, yeah.
My final year.
And can I ask then? You must be at a stage where you've got some pretty good conclusions from your work you've done. Can I ask what you found so far?
Yeah. So I've been quite focused on a particular eruption of Messiah volcano so far, which is the Messiah triple layer, which is the more recent eruption of the two that I've been studying, to look at what are the pre-acid eruptive conditions that might have promoted a Plinian eruption in this case. So by looking at constraining these conditions in the chamber and also in the conduit, to look at the idea that the pre-eruptive temperature is a moderate storage temperature, to say, so 1100 degrees or less. There's a lot of crystallization. This crystallization is occurring very fast during the eruption, and these conditions likely promoted the fragmentation of this magma during ascent, for the case of the triple layer. And then also looking at other constraints of what this condition was. So the volatile content, so how much water is there, and also the depth of storage before eruption, which is what I've been focused on till now, yes.
So are they quite rare then? Yeah. Because you need like the intersection of all these different components to come together at just the right sort of set of conditions.
Yes.
Yeah, I believe you published a paper earlier this year as well, Emily, with all these findings, which is really cool. So we can pop a link to that in the episode description.
Yes,
Yeah,
indeed.
sure.
Thanks.
But yeah, what's next for the rest of your PhD then? I know there's been a big spanner in the works with lockdown and everything. How has that been?
Different. Difficult in the sense of losing access to labs. Trying to like establish a working from home routine as well is different. But another aspect of my project is that I do numerical modeling. So kind of incorporating all of these conditions that I've been explaining into numerical models of magma ascent to see how this fits in with the physical processes that will be ongoing during ascent. And that I've been working on recently.
Is that almost the opposite of what you do, Marissa? Or is it the same thing that you do, but for the moon?
Let's see. So I suppose, Emily, if you've gotten all of your lab data, you're feeding that into the model then, aren't you? So I suppose that kind of the opposite. And I suppose at the end of the modeling, you'll probably then compare it to the real life samples and deposits.
Whereas you just make it all up.
Yeah, I throw numbers in, see what comes out, see what kind of deposits that would make.
And publish the paper.
Try and find pictures, draw some if I need to. Yeah, so I think they're similar in some ways.
Different in other ways, good.
Yeah, but me and Emily are using the same magma ascent model, which is quite cool to see it used in lots of different ways.
Yeah, versatile.
Yeah.
But it's good you've managed to at least use the time productively. And is it a massive redirection of the project, or is it something you're planning to do anyway?
No, it was something that's always been there. It's a large component of my work. So just shifting gears a bit to focus on that as well.
And I guess something we should really ask is, I guess we should ask this at the beginning. Obviously, volcanoes are super cool. So what was it that got you specifically into looking volcanoes other than them being super cool?
They are super cool, I would say. It's a big part of that. I think I kind of got my interest in high school, college, really. So when I first started looking at, I guess, plate tectonics, and then extending that to more earthquakes and volcanoes, which are hazards, specifically geophysical hazards, but I'm interested in essentially how the Earth system works and what that means for also communities who live in these areas. So I've always had that interest, I think, since then. And then I discovered geology as a subject that kind of brings all of these components together. So my undergraduate degree is in geology, following that. But I've always had the interest in volcanoes, I think, from that point. So it's been a long time.
So how many different volcanoes have you been to? And like, at what point in your life did you visit your first volcano?
Oh, that's a good question. I'm thinking back years now. Sorry. I think the first place I went to was Iceland. Actually, just to go and to be there, and then I went back for my master's project to work on some of the eruptions in the south of the island. But I think my first volcano visit was Mount Fuji.
Oh, really? That's cool.
Yeah. So climbing the volcano, you get like a huge sense of scale there.
Yeah, I'll bet.
That's very cool. Yes.
That's awesome.
Yes. and then I've been working in Messiah and Aetna, so I would say 4 or 5.
Mm-hmm.
Yeah, amazing. Have you ever been lucky or unlucky enough to experience any active volcanic activity?
So I've witnessed some activity, I guess, at Santiaguito, which is the active part of Santa Maria in Guatemala currently. It's a dome, and this produces explosions quite regularly. So I've witnessed that activity and observed that.
That's really cool.
That is really cool, yeah.
Mm.
So you said geology was essentially your first step really into getting into studying volcanoes. Did you know before you went to university that geology was an option at school? Obviously, we learn about it in geography at school. But yeah, did you know? Because I personally didn't know about geology before I came to university.
Yeah, I think that is true. My college did offer geology, but it wasn't something I was aware of until I was there. High school, no, I found it was in different subjects, so geography, science as well, covered some bits of sedimentology. But as a whole subject, I didn't really know until I was looking at options to study it undergraduate, and I was very interested in earth science in general. So I found myself in geology there. And then doing the degree, I found out a lot more other parts of geology. So I'm quite interested in volcanoes, but also igneous rocks in general, and petrology as a subject, which I would say I was not aware of until my degree.
So did you go straight undergrad onto the PhD, or do some things in between?
I did a master's in between, so this was a taught master's, the MSc. So there are some parts that are the taught course, and then you also do a research project as well, which I found very useful because after my undergraduate, I wanted to continue to specialize in an aspect of geology, which is volcanology. I was interested in research, but I didn't know exactly what that would mean on a day-to-day basis, or what the work would actually look like. So it was a really good opportunity to get some experience using instruments or to investigate a research question.
And that was on your Icelandic samples then, I assume?
Yes.
Yeah.
So this is an eruption, Eltica, in the south, Iceland, which is next door to Laki as well, but erupting a lot earlier, so 934 AD, 934, yes. But in a similar way, so these are very large volume basaltic eruptions, they're fissure eruptions. So they erupt along a segment, so like a large fissure or a large crack, essentially, producing large volumes of lava flows as well. And I was interested in sampling that deposit and looking at the eruption itself. So it's a bit different from what I work on now. That was a shift to the PhD, was looking at what do samples of explosives eruptions look like and how to sample them, which is different.
So what was it that brought you to look at this different side of volcanism? Because I assume there must have been a lot of projects out there on Icelandic volcanoes. But if you thought, did you just think, I'm hanging up my hat on that side of the subject, I'm ready to move on now?
I think I was really attracted by the PhD project, both because I'm interested in looking more at the explosive eruption, but also the method. I like the fact I've been able to do field work, I've done some laboratory work, I do some numerical modeling. It's given me a lot more exposure to things that I didn't have skills in before. I can use a lot more instruments, and being a geologist, I do like the fieldwork part. It's a very exciting part when to see the area that you're reading about in the literature is very nice.
Grand. Well, I guess I don't know. I don't want to cut any of you guys off, but I think it's time, isn't it, to ask the
final question.
Yeah.
Indeed.
Go for it, Ricky.
Oh, thank you. So we've discussed your awesome career in volcanics and getting to go out and see amazing things, but God forbid, of course, if you couldn't carry on doing that, what other career do you think you'd want to pursue?
It's a big question.
You can take your time to think about it. All right.
I think I always like the idea of science writing. I guess it's something similar. I guess still looking at science, but I'm quite interested in communications as well. So I guess that'll be something I'd be interested in if I wasn't looking at volcanoes.
Yeah, I mean that's pretty good. It's such an important, role to play, isn't it? Is the communication of this.
Wait, science communication, John, is important.
Yeah, who knew?
It's almost as though we're doing a podcast.
Yeah, is this being recorded? Oh, that's awkward.
Amazing. Well, thanks so much, Emily. It's been really, really interesting to talk to you. And best of luck with the rest of your PhD work. I'm sure you'll do great.
Thank you. Thanks for having me on the podcast.
You're very welcome.
Yeah, it's our pleasure.
Wonderful. So thanks everyone for listening at home. And if you're interested in getting more Earth and planetary science content, we're on Facebook, Twitter, Instagram, and we also have a blog. Links will be in episode description. But until next week, take care everyone. Goodbye.
Bye.
Bye.